Hello, dear student. Welcome to our channel that is NCRT Reader. And in this video, we will discussing about the KTG topic as well as thermodynamics. So this is one of the important chapter of the heat and thermodynamics as syllabus is given in J Main and J Advanced. So these are the formula rapid revision through which you can go through and remember while you are solving the question in J Main or J Advanced, because there we can't derive the formula over there. It will save our time. Once we remember that one, it will save the time so that we can go faster and get the maximum percentile over there. So let's have a look of this very first topic. It is pressure exerted by a gas. प्रेशर कैलकुलेशन के लिए जो फर्स्ट फॉर्मूला है वो है 1/3 m/v and mean square speed is that is mean square speed. So this is what m is mass of the enclosed gas here you can see, and v is volume of the container what will be taken over there. So on the basis of that you can calculate that pressure of the gas. Pressure will be there. How you can ask that how pressure will be there in the container if gas is kept inside the container. There will be many collision between the gaseous molecule and the wall of the container with the gaseous molecule. So if collision is there, force must be there, and if force is there and there we have the gas container wall, it is, so definitely pressure will be there. So what the pressure exerted by the gas on the wall of the container, you can see this is 1/3 m/v, and then mean square speed. Mean square speed you can write in terms of VRMS also. Sorry. As we know that VRMS is nothing but it is a square then mean then root of that one. So once you square of that, it is VRMS square. So it is pressure is 1/3 m/v and then VRMS square. This is one of the formula for pressure in terms of VRMS, and the mass of the container, mass of the gaseous molecule enclosed over there, and volume of the container. Now we can relate this mass in terms of Avogadro number and the mass of one molecule. So and this is mass of the gaseous molecule, and that you can have the mass of one molecule and then Avogadro number, that will be the mass of the gaseous molecule total over there. So once you replace with that form, it is we can have the density. Density is mass by volume formula. So what the this term we are having this is it is density of the gas, we can say here. So this is 1/3 and then density and then VRMS square. So this is another term, pressure in terms of density and VRMS. Then we have a speed of the gaseous molecule. So speed mainly it start with the root mean square speed. This is on the basis of result of Maxwell gaseous distribution law. And from there we have written this, just the formula it is, you need to remember that formula. So this one is one of the V1 square, V2 square, Vn square, so on divided by n. So this is a square, then mean, then root. So it is a square, then mean, then root. It is called VRMS. So this is another term, VRMS you can write in terms of the in terms of the gaseous constant R, temperature absolute, and the molecular weight of the gas. In terms of that, it is 3 RT by M. And you can change this in terms of pressure and the density also. Sometimes it is asked you in terms of Boltzmann constant. So Boltzmann constant is R gaseous constant divided by Avogadro number. On the basis of that, you can write VRMS in terms of Boltzmann constant, where K is Boltzmann constant and M is mass of one molecule over there. So this is all about the VRMS. Next speed we are having, that is average speed. So this is average speed. Average speed we write normally in terms of it is V1, V2, V3. The very basic concept, what you know, that it is average of all the speed of the gaseous molecule. Average, how we can write this is average speed. But mainly this type of concept, it is normally not asked to the question. It will be in average speed. They will be having on the basis of Maxwell distribution law, and it is 8 RT by pi times of molecular weight of the gas. So this one is the main concept, and if you remove this in terms of the pressure and density, so you can write this is to be 8 times of P, and then we have pi times of rho. So this is the in terms of pressure and rho, you can write over there. Then we have average speed. After that, most probable speed. These are the only three speed which you need to remember over there on the basis of Maxwell distribution law. It is so the most probable speed. Most probable speed. This you can write in terms of this is MP, most probable speed, and this will be in terms of, if I'll write in terms of temperature and then molecular weight, it is 2RT divided by MW. This one. So this you can write in terms of pressure also. So it is 2P by rho. The same thing I have written there in terms of RT by MW can be replaced by, it is P by rho. It is RT by MW can be replaced by, it is P by rho only. So here also you'll be having same relation. So this, but if I want to write in terms of Boltzmann constant, so how I can write over here, it is in terms of Boltzmann constant. So this will be, it is 2, then we have Kt by small m. Small m is the mass of one gaseous molecule. And here also you can write in terms of this Boltzmann constant. This will be RT by m. It is KT by m. It is. So when you can change this in Boltzmann constant, this will be, it is 8 Kt divided by m. In terms of Boltzmann constant, this will be the average speed. In terms of Boltzmann constant, this most probable speed. And in terms of gaseous law and the molecular weight, you can write like this. So these are the speed relations. So you can have the order. If you check the order of magnitude of which one will be greater one here. So order of magnitude will be, order of magnitude, we are having this VRMS will be the maximum one. Then we have average speed. Then we have most probable speed. Then we have most probable speed. So this is the order. If you want to write the order ratio, it is, so this VRMS ratio V average, then ratio V most probable. What will be the ratio here? You can see in all terms we are having that RT by M. Here also in terms of average also it is RT by M. And then here also you can see most probable it is RT by M. So what is the remaining factor? It will be, that is the ratio you can write off here. It in 3 root 3, and then we have, it is 8 by pi times, it will be root inside the root, and then we have root 2. So one you can simplify it finally. So it will be in terms of root 3. Then we have it is 8 by divided by 3.14, and then root inside it is almost close to 2.5. It will be, you can see here, and then we have root 2. So this will be having the root 3 factor. Here it is having root 2.5 times factor, and then here we are having root 2 factor. It is, so the most probable speed will be the having the minimum magnitude, and the RMS is having the maximum magnitude. Now with the gaseous speed, speed of gaseous molecule will be based, question will be based on this much concept only. So you can go through the question which is already asked in JMN kind, and you can practice over there that what kind of question it is asked. Then we have kinetic interpretation of the temperature. Kinetic interpretation of the temperature. So in this topic, we'll be learning about the what will be the kinetic, what will be the energy of that gaseous molecule. We know that gaseous, it is considered to be the kinetic energy mainly, and that we write in terms of change in internal energy. And gaseous molecule won't be having any kind of potential energy. It is considered to be our, because we neglect the, in kinetic theory of gases, we neglect the gravity over there, and on the basis of that it won't be having any potential energy. Mainly it will be having in internal energy, what you can say, and that internal energy will be the energy, kinetic energy, the potential energy of the molecule. But potential energy, if you check it out, that in ideal gas law, it is internal energy will be the total kinetic energy, and potential energy is considered to be zero over there. So for gaseous molecule, what will be the change in internal energy? You can write over here, it is change in internal energy. What will be change in internal energy? We denote it by delta U, and this is F divided by 2 times NR delta T, where F is degree of freedom. That I'll discuss later. So F by 2 it is, and then you can write here it is P2 and V2 minus of P1 V1. This is one way to write the change in internal energy, or in terms of temperature. Here you can write this one. This is in terms of pressure and volume we are having, and this is in terms of number of mole, and then we are having this temperature it is. So here F I have written, that is degree of freedom. So you can have degree of freedom analysis here. Degree of freedom. So degree of freedom is what you can say. It is many ways we have degree of freedom depending upon the gaseous characteristic. It is monoatomic, diatomic, non-linear, polyatomic. What kind of gas it will be? It will be having that kind of degree of freedom. So degree of freedom, one can refer to the number of possible ways in which a system can have energy. That is the meaning of degree of freedom. So it is number of ways in which a system can have energy. Number of ways here, it referred to the number of possible ways. So that we need to understand. If gas is for monoatomic, if I'll write here, it is monoatomic. If it is monoatomic means like that kind of gas where it is helium kind of gas. If it is argon, that these are the gas which are considered to be monoatomic. So for monoatomic, degree of freedom for monoatomic will be, it will be 3. And this 3 monoatomic energy will be only translational kind. If it is translational, it will be having all directions, X, Y, Z direction. Energy can move in X direction, Y direction, and Z direction it is. That is why for monoatomic, we consider only 3 degree of freedom over there, and all energy are that translational energy only. But for, if I go for the diatomic, it is, so for diatomic, if it is diatomic gases, so for diatomic gases, for monoatomic gas, what I have written here, it is what for diatomic gases, it will be kind of gas. What is H2, O2, N2? These kind of gases will be diatomic gas. So for this kind of gases, it is F diatomic will be, this will be 3 plus 2, 3 plus 2. So what is that 3 plus 2? It is 5. In 5, we have 3 translational. So in this case, we have 3 translational, and 2 vibration, 2 rotational, 2 rotational, 2 rotational. It is rotational, 2 rotational and 3 translational. So in this case, you can see here we have. So for diatomic gases, we can write F diatomic will be 3 plus 2, and that is here 3 is the translational, as well as here 2 rotational will be there. In one direction, we don't have that direction, the diatomic gas, that kinetic energy. So only 5 degree of freedom will be there, in which the that gaseous molecule, if it is diatomic, it can share its energy. That is the ways in which it can what you say, it can transfer the energy, that we can say here it is. Now we have polyatomic. For polyatomic type, we have CO2, it is NH3, this kind of thing will be there. If the gaseous molecule will be polyatomic kind, then we have, for polyatomic, degree of freedom will be, this will be 5. When it will be 5, for that kind of thing, if it is supposed to be linear kind of molecule, linear molecule. So if it is linear molecule, then we have like CO2 structure, CO2 structure. So for that, we have 3 translational and 2 rotational. So by that time we have degree of freedom 5. So CO2 can, what you can say for CO2 can share the energy. CO2 can share the energy in all uh, possible ways are 5 only. The 3 translational and 2 rotational. That is the meaning here. Degree of freedom for polyatomic, once it is linear, then it will be 5. And it is 6 when it will be 6 for non-linear. For non-linear, it will be 6. What kind of non-linear structure we are having? Like if you'll go for NH3. So if you go for NH3 kind of molecule, this is non-linear molecule. So in this case, we have 3 translational degree of freedom and plus 3 rotational degree of freedom. So in this case, we are having both degree of freedom, rotational and translational, maximum value in all direction, all dimension, it is XYZ. So it will be 6 only. Sometimes it happens that we are having polyatomic 7 also. That 7 can be considered, this is at higher temperature. At higher temperature. And when we consider higher temperature for linear molecule also, for linear molecule like CO2, if it is like CO2, if I'll consider. So for CO2 kind of molecule also, why it happens 7 at higher temperature is we are having 3 translational. Here it is 3 translational. Then we are having 2 rotational. Then we are having 2 vibrational also. So in this case, we consider vibrational energy also, but this is rare cases we are getting, but it is at a high temperature. It will be, just remember, whenever it is high temperature, we consider vibrational also. Sorry. So in this case, these are the like ways to remember the degree of freedom, because degree of freedom is very important for the point of view advance, as well as whenever we have mixture, two gases mixture over there. By that time, if you want to find out the gamma mixture or degree of freedom mixture, so once you are not have aware with the monoatomic, diatomic, or any kind of atomic molecule, what the degree of freedom it is, you won't be able to find that kind of mixture degree of freedom. So this is very important degree of freedom it is. And the next topic we are having that law of equipartition of energy. Law of equipartition of energy. What is the law of equipartition of energy? Says here it is. So according to this law, you can understand that equipartition of energy, the total kinetic energy of a thermodynamic system consisting of large number of particles, if it is, that will be equally distributed according to the among all the degree of freedom, and hence you can say that the average kinetic energy of molecule of each degree of freedom will be. So each degree of freedom will have the kinetic energy. It is 1/2 kT. This is the each degree of freedom is having kinetic energy. Kinetic energy it is. So where K is called Boltzmann constant, and T is absolute temperature. This T is absolute temperature. So whenever we have n moles of the gas and degree of freedom F and its kinetic energy, you can write for n mole of gas. For n mole of gas with F degree of freedom. So by that time, what will be the kinetic energy? We can write over there. Kinetic energy will be, it is F 1/2 NFRT. So this will be the kinetic energy. Here it is 1/2 NFRT. So if it is monoatomic, then kinetic energy for monoatomic will be different. So for monoatomic, if I want to write monoatomic, so what will be the degree of freedom for monoatomic? It is 3. So kinetic energy for monoatomic gas, it will be 3 by 2 nRT if it is monoatomic. For diatomic, it will be for diatomic. So kinetic energy for diatomic, it will be degree of freedom for that is 5. So it is 5 by 2 nRT. So that is the thing you have to remember, that whenever equipartition of energy means that what the degree of freedom is having, each degree of freedom is having the kinetic energy half kT, each degree of freedom. So how many degree of freedom? For monoatomic it is 3, so it is 3 by 2 nRT. If in terms of nRT, if I write, then 1 by 2 NFRT is the degree of the kinetic energy. And then if it is monoatomic, 3 by 2 nRT. Then if it is diatomic, 5 by 2 nRT. Likewise, you can change the that degree of freedom over there. Then the kinetic energy will be changed, and then you can calculate the kinetic energy accordingly. Now we have molar specific heat in gases. How we can relate that one? Let's see this. Next. Molar heat. Sorry. Molar specific heat in gases. Molar specific heat in gases. So just now we have seen that it is kinetic energy, how we can write, but molar specific heat is the thing which we have learned there in that calorimetry chapter. Their heat can be written like heat can be written like ns delta theta or nc delta p. If in terms of molar heat, then we can write that q is equal to nc delta t. This we have already gone through the previous videos. If you don't, then you can check it out in previous videos. I have discussed that one, how to write the molar heat capacity and how to write the specific heat capacity. This in 1 or 2 minutes you can cover it. So at constant pressure, if I'll say your heat energy supplied to a gas is spent not only in rising the temperature, but you need to remember that it is expansion of gas against the atmospheric pressure. So that is the thing, at constant pressure, what will be at constant pressure. If I'll go for at constant pressure, we write this as Cp. So Cp can be written like delta Q, and this will be at constant pressure only. And then we have n times of delta theta here. Delta theta means change in temperature. So this you can write in terms of gamma also. So what will be in terms of gamma? It is gamma r divided by gamma minus of 1. So this relation is also there. You will be learning this later when you will go on through that, how to relate gamma over there. But just now I have written in terms of gamma also, where gamma is, this is called adiabatic exponent. So this gamma is actually, it is called adiabatic. In adiabatic process, you will be learning mainly about gamma. So it is adiabatic exponent. Mainly gamma, we are having one relation. It is Cp by Cv. So Cp I have written here. And once you go for Cv, it is. So go for Cv. Cv will be at constant volume. So whenever we go for constant volume and constant pressure, we have Cp and Cv over there. This is called molar specific heat. And at constant volume, we can have that delta Q at constant volume. It is heat change over there at constant volume, then number of mole, and then delta theta, change in temperature over there. So this you can write in terms of gamma, if it will be, then R by gamma minus 1. So you can see here what the ratio here we are having. Let's suppose equation 1 and equation 2. And then you can see what will be the gamma. It is Cp by Cv only. You can get the ratio that will be there. So relation between Cp and Cv, we are having that relation now we can see. But this is the thing you need to remember whenever you are getting the encounter with gamma and then gaseous constant Cp, you can write like this, gamma R by gamma minus 1. And if it is Cv, then R by gamma minus 1. These we will use frequently whenever it is needed for the next thermodynamic process, wherever it is needed to write Cp and Cv. This is important. So now we have relation between sorry, Cp and Cv. how we can relate Cp and Cv. The first relation, it is called Mayer's equation, that Cp minus of Cv is equal to R. And where you can see Cp must be greater than Cv. That is why we are having R value here it is. So from this relation, we can say Cp is greater than Cv. The second relation we are having, that just now you have seen that Cp by Cv is equal to gamma. This is second relation. And there is third relation, which is also in terms of degree of freedom. You can write Cv is equal to, this is F by 2, and then R it is. So Cv you can write in terms of degree of freedom, and then gaseous constant R. So on the basis of gaseous constant, on the basis of this, sorry, on the basis of monoatomic, diatomic, nonlinear, linear, that we can relate some chart over there. This is very important. If you remember this chart, you can have many questions in your hand, how you can solve over there. So you just see this chart, it is. So first term, we are having gaseous kind, what kind of gaseous molecule it will be. Then we have degree of freedom. So this will be F, here it is. Then we are having that delta U, what is the change in internal energy? It is degree of freedom by 2, then N R. What the kinetic energy we are having, that is only change in internal energy. And then we are having that CV value. CV value, just now you have seen that it is delta U divided by N and delta T. So from here you can write delta U as N CV dt. And then we have Cp value. We know that it is Cv plus of R. And then we have gamma value. So this gamma it is. Gamma is nothing but it is Cp divided by Cv. That will be gamma. One by one, we can see here that for monoatomic, if you want to write that value, so how you can write for monoatomic? Monoatomic. If it is monoatomic gas, then for that it is 3 degree of freedom. It is only translational degree of freedom. Just now we have seen it is. And for that, if you want to write the change in this internal energy over there, so this degree of freedom will be 3 by 2 N R delta T, here it is. Then for Cv, if you want to write here, it will be 3 by 2 R. And then it is Cp will be one more than that. It is 5 by 2 times of R, and it is 5 by 3. So this is the monoatomic gas. I have written everything you can get from there. Then you have diatomic gas. Diatomic gas. So if it is diatomic gas, then we have 3 translational kinetic energy, 3 translational energy over there, and then 2 rotational energy. So this will be 5 only. 5. So here you can write this is to be 5 by 2 nr delta T. This is the change in internal energy. And then we have a Cv value. It is 5 by 2 times of R, and then 7 by 2 times of R, and then it is 7 by 5. There are many times when I used to solve the question, then I forget to write what is Cv and Cv and all. But once you remember it, you won't be able to having any kind of difficulty in solving question. Rather than you don't know the Cv value, you won't able to solve the question. So that is sometimes it is needed to remember, and you can easily solve over there. So this is next we have non-linear, and or you can say it is polyatomic. Non-linear polyatomic, if it is non-linear plus polyatomic, and then what you can say 3 translational we'll be having, 3 translational plus 3 rotational. This will be, and in this case you can see 6 by 2, it will be 3, and then n r delta T. This will be the change in internal energy. Then we have 3r as Cv, and this will be 4r. And here we are having, this is 4 by 3. Sometimes it is given to you gamma value 4 by 3. You need to understand this is non-linear and polyatomic, and then that kind of things you keep inside your mind. Once you just see the 4 by 3 value, everything should be there in your mind that it is 4 by Cv will be 3r, it is 4r, and this is change in internal energy. This will be the degree of freedom over there. So that you can have any kind of question, difficult level or easy level, you can solve over there. This chart is very important to have with. Next topic we are having that when we mix up the two gaseous molecule having the number of mole given over there, and then degree of freedom of there, it will be given to you. Number of mole individual and degree of freedom if it is given to you, then how you find the mixture that degree of freedom. So for mixture, this is degree of freedom for mixture. How you can find the degree of freedom for mixture? Suppose I am considering two gaseous molecule. One is having that if it is gaseous molecule A, let's suppose this is I'm considering gas A, and it is having number of mole Na, and the degree of freedom if it is having Fa. So this is the number of mole here. It is mole of gaseous molecule, gas A it is, and then degree of freedom it is. And the other gas we are having that gas B. If I'll consider the other gas B, and it is having number of mole B, this will be the number of mole over there, and then degree of freedom B, degree of freedom B. And once you mix the both gases over there in a container over there, so mixture will be having, this is mixture of both. So what will be the degree of freedom for mixture? So here we can write that mixture is having degree of freedom, F mixture will be, this we can write like it is Na then Fa plus Nb then Fb divided by total number of mole. So it is Na plus Nb. Suppose three gaseous mixture will be there, you can add the third also. You can add the third in numerator and NCFC, as well as in denominator also Na plus Nb plus Nc. Likewise, you can change. If it is three gaseous molecule, 4 N molecule, you can add like this only. So in numerator, you can have the summation of number of mole and then degree of freedom. In denominator, we have total number of mole that will give you the F mixture, degree of freedom of the mixture. Then you have the second form to calculate in this one is gamma mixture. Sometimes this is the question asked. It is asked already in JMIN. I've seen there and in advance also. So you can write this is to be in terms of degree of freedom, what will be there. So what is that this mixture is having gamma mixture is, once you calculate degree of freedom of mixture, then you can calculate this also. This also you can calculate. Sometimes it is given that no degree of freedom in the question. So on the basis of gamma value, you can understand that what is the degree of freedom for it one. If it is gamma value is 7.5, this degree of freedom will be 5 here it is. If degree of freedom is, if gamma value is 5/3, then you can find that degree of freedom will be, it is translational only. And on the basis of that, you can find out. That is the thing you have to remember here. So next we are having this gamma mixture, F mixture, then we have CV mixture, the third one it is. CV mixture. So how you can find the CV mixture? In terms of F mixture only, we know it is F mixture divided by 2 times of R. Normally CV we can write this is in terms of degree of freedom, it is F divided by 2 times of R. But here we are looking for mixture, then F mixture will be there. And then fourth relation we are having that it is CP mixture. So once you are having CV mixture, you can easily calculate that CV mixture plus R value will be CP mixture. So these are the mixture relation whenever we are having mixing of two gases, three gases, four gases, or n gases, no matter at all. You can find first F mixture over there, degree of freedom for the mixture gas, then you find the gamma mixture, and then you can find CV mixture and CV mixture, or whatever the question is asking you, you can find out that. So this is called the mixture connection with the degree of freedom. And then previously what we have discussed, that was that molar specific heat capacity, and then it was kinetic energy, that law of equipartition of energy, and likewise a degree of freedom. Here it is started kinetic interpretation. So this is the topic which was important in kinetic theory of gases. Next topic we are having in this subtopic only. Next subtopic we are having that mean free path. Mean free path is actually defined as this is the average distance traveled or covered by molecule means gaseous molecule between two consecutive collision. So this is the thing you need to remember, that whenever we have mean free path, this is represented by the lambda. Here it is, and you can write this lambda. It is the this is called mean free path. It is actually distance covered by the molecule between the two consecutive collision. So you can write the lambda in terms of here number of molecules per unit volume and the density and number density over there, and then diameter of the molecule. How what it will be? It is 1 divided by root 2 pi, then we have d square into n, d square into n, where a small n represent here, this is number of molecules, this number of molecules per unit volume, per unit volume, or we can say it is simply, we can say that number density. That is the meaning of a small n here. And then we have a small d also. So a small d value, it is diameter of the molecule. The gaseous molecule diameter, it will be. So in terms of gaseous molecule diameter and the number of molecules per unit volume or the number density, you can write the mean free path, which is actually the distance covered by the gaseous molecule in two consecutive collision, between two consecutive collision, whatever the distance covered by the gaseous molecule between two consecutive collision will be there, that is called lambda value. And on the basis of that, you can have that it is inversely proportional. Here you can see that this is inversely proportional to the density of gas closed inside the container. So this is also lambda is inversely proportional to density of gas in a closed container. This you need to remember, that whenever lambda is there, this will be inversely proportional to the density over there. And you can see another relation with the temperature, that the second relation I'm writing. If we increase the temperature, if we increase the temperature, then lambda remains, here it is same. So sometimes it is confusion among the student that if we increase the temperature over there, that lambda value should be changed over there, but it is same. This you need to remember. So this was all about the, what we can say about the kinetic theory of gases. These are the topic which you need to cover for the JMN as well as for advanced. Advanced in type, we are having different some questions also there that I am not discussing here right now. Just going for revision concept as well as formula only, so that it will be there in your mind and you can hit the JMN kind of question. So problem segment we'll discuss later. Next, we are having that first law of thermodynamics. So this is the last part, last chapter of this heat and thermodynamics chapter. So it is first law of thermodynamics. In thermodynamics, So in thermodynamics topic, first law we are having that zeroth law we have already covered over there. So it was all about the talking you about the thermal equilibrium. It's the two body are in thermal equilibrium, A and B are in thermal equilibrium, and B and A and C are in thermal equilibrium. Then B and C will be in thermal equilibrium. That is zeroth law. And talking about the thermal equilibrium means it is having the same temperature. That is the zeroth law of thermodynamics. Then next, or the important one where it is to be noted over there, that is called first law of thermodynamics. First law of thermodynamics. First law of thermodynamics, it is mainly based on the conservation of energy, that you have to remember. Conservation of energy. It is based on conservation of energy. This is the first thing you have to remember. And whenever we increase the internal energy, that means increasing temperature will be there. Definitely, you have seen that one. And whatever the work done during expansion of the gas. So whatever the energy we are providing to the gaseous molecule, let's suppose we are providing delta Q energy to the gaseous molecule. This energy is supplied to the gaseous body. So if this energy is supplied over there to the gaseous molecule, if this much amount of energy is supplied to the gaseous molecule, then based on the this energy conservation or first law of thermodynamics, what will happen to this gaseous molecule is there will be increase in the internal energy. So you are providing some heat to the gaseous molecule, that happen that increase in internal energy. So increase in internal energy. Why this energy of gaseous molecule increases? Internal energy of the gaseous molecule increases, and I have written here why this internal energy of the gaseous molecule increases. The reason behind that is temperature will increase over there. So once you are providing that amount of energy, heat energy over there to the gaseous molecule, that what happened, that temperature of the gaseous molecule increase, due to which the internal energy over there it will increase. So this is the reason that we can say here, that is temperature here it will increase. That is the thing you need to understand. Then the second part you can see here in terms of work, if I want to write over there. So in the if I'll go for the work done by the gas, though, what is happening over there, work done by the gas, this will be work done by the gas during the expansion against the surrounding, so this you can say work done by the gas when it is expansion, during expansion. So this will be happening against the surrounding. So these things you need to keep in mind, that whenever heat we are supplying to the gaseous molecule, two things are happening over there. One, gas is getting expansion over there, and in the internal energy also increases. And the logic behind that is, one, internal energy increase means we are providing some energy, so temperature will increase over there, and work done is work done by the gas during the expansion is happening also there. That is the relation or equation what we can write on the basis of first law of thermodynamics is that we can have that relation delta Q is equal to delta U plus of delta W. This is the first law of thermodynamics what we are having, and on the basis of this law only numerous of problems you can solve over there on the first law of thermodynamics. Based only whatever the thermodynamic process we are having, you can solve all the questions of thermodynamic process based on this law only, because these are the thermodynamic parameter which can be calculated in the question, which can be asked, that what will be the heat, what will be the change in internal energy, what will be the work done over there. So first of all, we'll go for that one by one, how you can find the work done by a gas. So how we can find work done by a gas? Whenever we need to have calculation of work done by a gas, that you can understand that gas will be there here. Let's suppose this is one of the container, and here container is having some gas, and this is the piston of the container. Here gaseous molecules are there inside this pin. So there will be some pressure over there. Internal gaseous molecule will have some pressure applied on this this container, this piston inner part. It will be, let's suppose this is the P it is applying. If pressure is applying, due to pressure application, let's suppose that piston position has been shifted, and it is shifted somewhere here it is. So wherever it was having earlier position, now it is shifted by some amount over there in the direction of that pressure application, that let's suppose delta X I am considering here. So work done by the gas, what it will be, we know that it is work done by the gas. According to the definition of work done in mechanics, whatever we have learned, that only I'm applying here. This is F dot of dr or delta R. So what dr or delta R it will be? It will be F delta x, and the force and this pressure and the displacement is in the same direction. So we can write here it is delta x and then cos 0 degree, because you can see here force is parallel to the dr part. It is in the same direction of delta R or dr it is. So what you can say here, F dot del x, this will be the work. This will be the work. So this is what we are having the information on the basis of mechanics and how to find that work. But if I'll apply this whenever we have large change in volume, so in that case, we cannot apply this large change in volume. That by that time, this discussion of pressure will be uh, consideration in the picture. You have to consider the pressure consideration over there. So whenever we have large change in the volume, by that time, we cannot go for this force application over there. If this is a smaller displacement, we can go for that one. But if suppose large change in the volume of the gas will be there, can we apply this force to calculate the work? No, then we have to go for pressure application over there. So we can apply the pressure application. So work done by the gas, that work done you can write over there. This is F dot of dx, the same manner what we have written over there. But here this work, this force can be changed with the pressure applications. F, this is pressure times of area of cross section. If I'll consider that area of cross section of this piston is A over there, so this will be PA times dx and then cos 0. So this will be the integration. Now you know that this is area into dx. It is nothing but the volume part over there. So what the volume it is? It is pressure times of dV. So integrate this one. Now this is the limit here. You can write that it will be from V1 to V2. If it is integrating, then we can have that work done by the gas over there. So work done by the gas, we can calculate on the basis of PdV, V1 to V2. This is one. So sometimes in question, it will be asked that work done by indicator diagram. So work done by indicator diagram, you can use work done by indicator diagram. What we can say here, it is work done by indicator diagram. In this indicator diagram says you something about the graph between pressure and volume. That is called indicator diagram. So on the basis of pressure and volume diagram, this is you can have this is as volume axis, and this as pressure axis. And let's suppose I consider this could be the graph of the pressure volume relation over there. It is. So you can see here this point we are having the pressure 1. This is P1 point, and this is having the corresponding pressure point. It is P2, and here we are having that volume. It is V1, and here we are having the volume. It is V2. So what will be the, here you can see area under the curve. If you go for the area under curve, the pressure and dV, if you go for, then we can find the area. So you can write the this work done from A to B. If I'll consider this point to be A and this point to be B here. So in this indicator diagram, what will be the work done during the gas? If it is expansion, if it is expanding from A to B, volume is getting increased. So you can write that work done in the shown figure from A to B will be work done from A to B. If it will be going, that we know that it is P dV, and then we integrate it from V1 to V2. So this is nothing but it is called area under this graph. It is area under PV curve. So it is area under pressure volume graph. That is simply you can go for the work done in a particular process over there. If it is any kind of process, it is no matter pressure volume graph, it is given to you. So you find the area under that pressure curve on volume curve, you will be getting that area. So what will be the area under this curve? This will be the area of this part. It is, you can see here, these are the part for which you can find the area. These are the part it is. around the curve I am considering, and then this pressure and volume axis it should be considered to be. So these are the area which can be calculated. That is your exact area which you should think of. This is the area actually we are looking for here. It is, and what the area it will be? This area will be the work done by the gas during process A to B. Likewise, you need to remember that. If suppose pressure axis will be given on x-axis and volume will be on y-axis, then what to do? So this could be the possibility that you are having given that pressure on x-axis and volume on x-axis. Then also you will do the same. Let's suppose I am considering any graph like this. Wait. Let's suppose I am considering any graph like this. If this is the graph and the process is from this point to this point, this is the process happening over there. So what the you will be getting area under the curve of P and V will be. This one is the area point you have to consider of. So suppose this I am considering that it is starting from this point I point, and this is F point, final point it is. So what will be this is your V initial, and this is your V final. So what the area you'll be getting here, this is the area part here, what we are having, that will be the area under PV graph, and that will be the work done. That will be the work done. So here we are considering the area to be on a y-axis because pressure is given on x-axis. That is why it will be. So this area you have to calculate, and this area is the what we can say that it is the work what is we are looking for. So this is the work you can find out. जब भी आपको प्रेशर और वॉल्यूम ग्राफ दिया हुआ रहेगा तो इसको हम इंडिकेटर डायग्राम बोलते हैं, और इसमें एरिया अंडर कर्व निकालेंगे तो हमें वर्क मिलेगा। जिस प्रोसेस के लिए दिया हो रहे हैं, अगर वाई एक्सिस पे वॉल्यूम कर्व दे दिया गया है और एक्स एक्सिस पे प्रेशर, तो इस तरह से जो एरिया आएगा दैट विल बी योर वर्क डन बाय द गैस। ये चीज ध्यान रखना है। अब फर्स्ट लॉ ऑफ थर्मोडायनामिक्स जो है वो लॉ ऑफ कंजर्वेशन पे बेस्ड है, यानी कि जो भी हीट हम प्रोवाइड करेंगे गैसेस मॉलिक्यूल को सप्लाई करेंगे, वो जो है दो ही तरीके में कन्वर्ट होगा वो हीट। एक तो इंक्रीज इन इंटरनल एनर्जी में जाएगा जिससे कारण से गैस का टेम्परेचर बढ़ जाएगा, और दूसरा वर्क डन बाय द गैस होगा क्योंकि वहां पे एक्सपेंशन हो रहा है तो वो अगेंस्ट द सराउंडिंग हो रहा है। तो जो भी एनर्जी हम प्रोवाइड करेंगे गैसेस मॉलिक्यूल को, वो इंटरनल एनर्जी को चेंज करेगा और वहां पे गैस जो है आपको वर्क कर रहा है। तो दो पार्ट में एनर्जी, हीट एनर्जी जो सप्लाई होगा वो जाएगा। तो कुछ चीजें दिमाग में रखना है कि अगर आपको पॉजिटिव है निगेटिव है तो कैसे साइन कन्वेंशन होगा, बिकॉज समटाइम्स इट इज गिवन दैट हीट सप्लाइड हीट गेन हो रहा है तो क्या हो रहा है नहीं हो रहा है। तो ये चीज ध्यान रखना है कि अगर Q का वैल्यू पॉजिटिव है तो इसका मतलब हुआ कि हीट इज सप्लाइड एंड कहाँ पे सप्लाइड हुआ है? टू द सिस्टम। अगर पॉजिटिव हीट दिया हुआ है तो इसका मतलब ये है कि हीट जो है सप्लाई किया जा रहा है किसको? सिस्टम को। दिस इज द फर्स्ट पॉइंट यू हैव टू कीप इन माइंड। देन इफ Q इज नेगेटिव, इसका उल्टा हो जाएगा। इस केस में क्या होगा? हीट इज रिजेक्टेड बाय द सिस्टम, यानी कि सिस्टम को ही ध्यान में रखते हुए या तो सिस्टम में जा रहा है या सिस्टम से जा रहा है। ये चीज ध्यान में रखते हुए Q को पॉजिटिव और निगेटिव आपको दिमाग में रखना है। जब भी Q पॉजिटिव होगा तो हम हीट सप्लाई कर रहे हैं किसको? सिस्टम को। Q निगेटिव होगा तो सिस्टम हीट सप्लाई कर रहा है, रिजेक्ट कर रहा है, उसी को मतलब हुआ कि सिस्टम हीट को रिजेक्ट कर रहा है। दैट इज द मीनिंग। नेक्स्ट पॉइंट यू नीड टू माइंड कीप इन माइंड दैट डेल्टा यू जो है ये चेंज इन इंटरनल एनर्जी है। तो डेल्टा यू जिस समय प्लस आ रहा है आपका प्लस, तो इस समय आपको ये चीज ध्यान रखना है कि ये हम तब बोलेंगे जब इंक्रीज होगा इंटरनल एनर्जी। दैट इज द मीनिंग। सो ऑन इंक्रीज इन द इंटरनल एनर्जी, इन इंटरनल एनर्जी, ऑन इंक्रीज इन इंटरनल एनर्जी, ये चीज ध्यान रखना है। और अगर यही चीज निगेटिव हो जाएगा तो जस्ट उल्टा। तो इस केस में हो जाएगा ऑन डिक्रीज इन इंटरनल एनर्जी। नेक्स्ट वी आर हैविंग दैट अबाउट द वर्क ऑल्सो। तो वर्क अगर पॉजिटिव होगा तो उस केस में क्या कहेंगे, जब भी डेल्टा डब्ल्यू को अगर कंसिडर करते हैं वर्क में, तो अगर ये पॉजिटिव है तो इसमें हम कहेंगे कि ये तब होगा पॉजिटिव जब एक्सपेंशन हो रहा है गैस का, और वर्क डन जो है, वर्क डन एक होता है बाय द सिस्टम ऑन सराउंडिंग, और एक होगा वर्क डन बाय द सराउंडिंग ऑन सिस्टम। तो यहाँ पे जब भी पॉजिटिव होगा तो इस केस में हम बोलेंगे ऑन एक्सपेंशन। दिस इज फर्स्ट थिंग यू हैव टू रिमेंबर, दिस विल हैपन ऑन एक्सपेंशन। एंड इस केस में जो है वर्क जो कर रहा है वो आपका वर्क इज डन बाय द सिस्टम, बाय द सिस्टम। तो जब भी वर्क इज डन बाय द सिस्टम होगा, किस पे वर्क हो रहा है, ऑन द सराउंडिंग। तो उस केस में हमें ये चीज ध्यान रखना होगा कि वर्क डन जो है वो पॉजिटिव होगा। और फिफ्थ केस है कि वर्क डन अगर निगेटिव हो गया तो, निगेटिव हो गया तो इस केस में क्या होगा, यहाँ पे जो है एक्सपेंशन नहीं होगा, यहाँ पे कंप्रेशन होगा, यहाँ पे कंप्रेशन होगा। तो ऑन कंप्रेशन, यानी कि कंप्रेशन जब भी आप करेंगे तो कंप्रेशन कब होगा, जब वर्क डन कौन करेगा, वर्क डन, वर्क डन बाय द सराउंडिंग, बाय द सराउंडिंग, वर्क डन बाय द सराउंडिंग ऑन द सिस्टम। तो लैंग्वेज को क्वेश्चन में ध्यान से देखेंगे, उससे आपको पता चलेगा कि वर्क डन पॉजिटिव होगा या निगेटिव होगा, डेल्टा यू पॉजिटिव होगा या निगेटिव होगा, क्यू जो है निगेटिव होगा या पॉजिटिव होगा। ये चीज आपको इस लैंग्वेज पे ध्यान रखना है। एक बार फिर से आप देखिए, क्यू पॉजिटिव का मतलब है हीट इज सप्लाइड टू द सिस्टम, क्यू निगेटिव का मतलब है हीट इज रिजेक्टेड बाय द सिस्टम। डेल्टा यू पॉजिटिव का मतलब ऑन इंक्रीज इन इंटरनल एनर्जी, डेल्टा यू निगेटिव का मतलब है ऑन डिक्रीज इन इंटरनल एनर्जी। एंड डब्ल्यू अगर पॉजिटिव है तो ये तब होगा जब एक्सपेंशन होगा, वर्क इज डन बाय द सिस्टम ऑन सराउंडिंग। तो जब भी एक्सपेंशन होगा और वर्क इज डन बाय द सिस्टम कहा जाएगा, तो उस केस में जो है पॉजिटिव होगा वर्क डन। और वर्क डन निगेटिव का मतलब ऑन कंप्रेशन पे वर्क डन निगेटिव होगा, वर्क डन बाय द सराउंडिंग हो रहा है यहाँ पे ऑन द सिस्टम। So these things you have to remember. Also one thing, you can have that option, many option में जब भी रहता है तो theoretical part आपको रहना चाहिए। तो इसमें Q एंड W जो है, ये दो फंक्शन आपको दिख रहा है, Q हीट है और W वर्क है। ये दोनों जो है पाथ फंक्शन है, पाथ फंक्शन है। पाथ फंक्शन का मतलब क्या होता है, जो पाथ पे डिपेंड करेगा, पाथ पे डिपेंड करेगा। तो पाथ पे डिपेंड जब भी करेगा तो वो किस प्रोसेस का है उस पे डिपेंड करेगा, यानी कि ये टाइप ऑफ प्रोसेस पे डिपेंड कर जाएगा। टाइप ऑफ प्रोसेस, प्रोसेस मतलब किस टाइप का प्रोसेस है। थर्मोडायनामिक प्रोसेस में बहुत तरह का प्रोसेस अभी हम लोग देखेंगे, उसके बेसिस पे आपका वर्क चेंज करते जाएगा और हीट भी चेंज करेगा, ये चीज ध्यान रखेंगे। लेकिन दूसरा टर्म जो हमारे पास है, यानी कि चेंज इन इंटरनल एनर्जी जो है डेल्टा यू, डेल्टा यू जो है इसको हम लोग बोलते हैं स्टेट फंक्शन। इट इज स्टेट फंक्शन। स्टेट फंक्शन का मतलब क्या है कि ये मात्र इनिशियल पॉइंट और फाइनल पॉइंट पे ही डिपेंड करेगा, पाथ पे डिपेंड नहीं करेगा। तो दैट मीन्स इट डिपेंड्स ओनली ऑन इनिशियल एंड फाइनल स्टेट्स ऑफ सिस्टम। इट ओनली डिपेंड्स अपॉन द इनिशियल एंड फाइनल स्टेट्स ऑफ द सिस्टम। ये चीज आपको ध्यान में रखना है। और इसी के बेसिस पे जो है आप आगे जो भी साइन कन्वेंशन को यूज करेंगे, इसमें प्लस माइनस कहाँ पे क्या दिया हुआ है, तो यू नीड टू अंडरस्टैंड द थिंग्स व्हिच आई हैव ऑलरेडी डिस्कस नाउ। अब आते हैं थर्मोडायनामिक प्रोसेस पे। यहाँ से स्टार्ट होता है कौन कौन प्रोसेस है आपको थर्मोडायनामिक्स में। लेट्स सी, इट इज थर्मोडायनामिक प्रोसेस। थर्मोडायनामिक प्रोसेस में जो है सबसे पहला प्रोसेस हम लोग देखते हैं मेल्टिंग, मेल्टिंग प्रोसेस। मेल्टिंग प्रोसेस के बारे में हम जानते हैं कि यहाँ पे क्या होगा, जब भी मेल्टिंग होगा तो यहाँ पे स्टेट का चेंज होना जरूरी है। तो यहाँ पे चेंज ऑफ स्टेट होगा, और किस स्टेट से किस स्टेट में जाएगा, मेल्टिंग हो रहा है तो ऑब्वियस सी बात है सॉलिड से लिक्विड में जाएंगे। ये स्टेट जब भी चेंज होगा इसको मेल्टिंग बोलते हैं, ठीक है। तो मेल्टिंग में अगर हम फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स लगाएं तो क्या होगा? अगर हम फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स को लगाएं तो क्या होगा? तो मेल्टिंग हो रहा है तो यहाँ पे लेटेंट हीट ऑफ, क्यों लेटेंट हीट? क्योंकि फेज चेंज हो रहा है, टेम्परेचर तो चेंज होगा नहीं, बिल्कुल नहीं होगा। तो यहाँ पे लेटेंट हीट होगा, हीट के लिए हम यूज करेंगे MLF, दिस इज मास ऑफ दैट, जो भी सॉलिड को मेल्ट किया जा रहा है, एंड यहाँ पे लेटेंट हीट ऑफ फ्यूजन, दिस विल बी डेल्टा U। और यहाँ पे वर्क डन होगा? नहीं होगा। क्यों नहीं होगा? तो वर्क डन नहीं होगा, इसके पीछे का राज ये है कि वर्क डन यहाँ पे जीरो हो रहा है। क्यों? क्योंकि वॉल्यूम जो है, वॉल्यूम चेंज नहीं कर रहा है, वॉल्यूम रिमेन्स कांस्टेंट, दिस इज कांस्टेंट। तो जो सॉलिड का वॉल्यूम था और जो आपका लिक्विड बन रहा है, इसके वॉल्यूम में जो है आपको कोई चेंजेस नहीं हो रहा है, इस कारण से यहाँ पे वर्क डन जीरो होगा। क्लियर? अब दूसरा पार्ट है इसमें, आपको मेल्टिंग में हमें ये चीज ध्यान में रखना है, मेल्टिंग जब भी होगा तो यहाँ पे फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स का मतलब जो हीट सप्लाई आपने कर रखा है, किया, वो हिडन लेटेंट हीट ऑफ हीट होगा, और वो सारा का सारा टोटल चेंज इन इंटरनल एनर्जी में चला जाएगा, क्योंकि वर्क तो हो ही नहीं रहा है, तो वो चेंज इन इंटरनल एनर्जी में चला गया। ठीक है। दूसरा प्रोसेस है हमारे पास, मेल्टिंग के बाद जो प्रोसेस है वो है इस केस में बॉइलिंग का, बॉइलिंग प्रोसेस, लेट्स सी इट इज। तो बॉइलिंग प्रोसेस में भी हम जानते हैं कि जब बॉइलिंग होगा तो उस केस में भी चेंज ऑफ स्टेट होगा, कौन सा स्टेट से कौन सा स्टेट में जाएगा, चेंज ऑफ स्टेट होगा। इसमें लिक्विड से वेपर होगा, लिक्विड से वेपर। तो जब लिक्विड से वेपर जाएंगे तो इस केस में क्या, हम यहाँ पे जो फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स को यूज करते हैं, डेल्टा Q इज इक्वल टू डेल्टा U प्लस W, यहाँ पे इस केस में अगर हम यूज करना चाहें इस रिलेशन को, तो क्या हम इसमें इसको यूज कर सकते हैं? बिल्कुल। तो बॉइलिंग प्रोसेस में हमें यहाँ पे चेंज ऑफ स्टेट जो हो रहा है वो लिक्विड से वेपर में हो रहा है, और इस केस में हमारे पास जो फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स को अगर हम लोग यूज करते हैं, तो हमारे पास क्योंकि यहाँ लेटेंट हीट ऑफ वेपोराइजेशन यूज होगा, तो जो हीट आप दे रहे हैं वो M×LV में जाएगा, दिस हीट जो है वो M×LV होगा, और फिर चेंज इन इंटरनल एनर्जी होगा। क्या यहाँ पे वर्क जीरो होगा जो कि मेल्टिंग में जीरो हो रहा था? नहीं होगा। क्यों नहीं होगा? तो क्यों नहीं होगा, इसके पीछे का राज बताते हैं। इसीलिए नहीं होगा क्योंकि यहाँ पे जो V2 और V1 आप देख रहे हैं, V2 जो है ये वॉल्यूम है किसका? वॉल्यूम ऑफ वेपर, वॉल्यूम ऑफ वेपर। इसमें क्या अंतर हो गया? अगर हम V1 का बात करें तो ये हो गया वॉल्यूम ऑफ लिक्विड। तो वॉल्यूम ऑफ वेपर और वॉल्यूम ऑफ लिक्विड में चेंजेस है, तभी तो ये वर्क नहीं जीरो हो रहा है। क्या चेंजेस है? कैसे हम ये मान ले कि वॉल्यूम ऑफ लिक्विड और वेपर जो है वो चेंज कर रहा है? तो जब आप 1 ग्राम वाटर को वेपोराइज करोगे, 1 ग्राम वाटर है, और इसको अगर हम वेपोराइज करते हैं, 1 ग्राम वाटर इफ इट इज वेपोराइज ओवर देयर, जैसे ही इसका वेपोराइजेशन होगा, ऐसोबारिकली, ऐसोबारिकली क्या है ये हम आगे पढ़ेंगे। ऐसोबारिकली होता है प्रेशर कांस्टेंट। तो इसका टेम्परेचर हम मान लेते, प्रेशर मान लेते हैं कि हम लोग 1 एटमॉस्फेयर रख रहे हैं, और 1 ग्राम वाटर को हम लोग वेपोराइज कर रहे हैं। तो इसमें चेंज इन इंटरनल एनर्जी जो होता है, दिस इज 191 जूल जो है आपका एनर्जी इंटरनल में चेंजेस होता है, ये चेंजेस हो रहा है आपको। और वॉल्यूम जो अगर हम 1 ग्राम वाटर का देखें, तो अगर इसको हम सेंटीमीटर में लिखना चाहें तो दिस इज 1 सेंटीमीटर क्यूब। And V2, if you calculate on the basis of this one and what we are providing this M and LV, we know that it is. So on the basis of that, you will calculate the work done, and then we can find out what will be the volume V2 over there. So V2 वहां से calculate करके 1671 के आसपास आपका ये निकल रहा है, 1671 it is meter cube. This one we are getting here, it is. सो यू कैन इमेजिन यहाँ पे वॉल्यूम ऑफ लिक्विड 1 cm³ है और ये निकल रहा है, तो ऑब्वियस सी बात है वर्क डन जो है जीरो नहीं होगा। और उसी कंसेप्ट को हम लोग यूज करेंगे बॉइलिंग में, और इस चीज को ध्यान में रखेंगे। तो बॉइलिंग में जो कंसेप्ट यूज होगा वो यही कंसेप्ट यूज होगा। नेक्स्ट प्रोसेस है हमारे पास, जो अब प्रोसेस है वो है आइसोबारिक आइसोकोरिक लाइकवाइज इट इज। सो पहला हम लोग देखते हैं आइसोबारिक प्रोसेस। तीसरा, पहले था मेल्टिंग, दूसरा बॉइलिंग, तीसरा आइसोबारिक। आइसोबारिक का मतलब ये हो जाता है कि प्रेशर जो है ये कांस्टेंट होगा, प्रेशर विल बी कांस्टेंट। ठीक है, अगर प्रेशर कांस्टेंट है तो हमारे पास जो वर्क निकालने का फॉर्म है उसमें हम लोग यूज करते हैं पीडीवी। तो इसमें प्रेशर को तो कांस्टेंट ही रख लिए, तो पीडीवी को फिर क्या करेंगे, चेंज करेंगे किसमें, तो पी को हटाओ यहाँ से क्योंकि कांस्टेंट है, तो इसको आप ले आओ टेम्परेचर के टर्म में, तो इट विल बी पी डी वी को हम लोग लिख सकते हैं, इट इज डेल्टा टी एन आर डेल्टा टी इन टर्म्स ऑफ व्हाट यू कैन से नंबर ऑफ मोल एंड द टेम्परेचर इट इज। तो Q को अगर हम लोग यूज करेंगे, Q इज हीट इट इज, तो ये हो जाएगा यहाँ पे एन सी पी एंड देन वी हैव डेल्टा टी। जब भी हम एसओ बारीक में हीट को निकालेंगे तो ये फॉर्म यूज करेंगे, और ये आएगा कैसे, तो इसको हम लोग लिखते हैं डेल्टा यू प्लस ऑफ डब्ल्यू। तो डेल्टा यू क्या होता है, डेल्टा यू आपका होता है एन सी वी डेल्टा टी, और पी क्या वर्क डन क्या होगा, तो ये अभी हम लोग देखें एन आर डेल्टा टी। तो यहाँ से एन डेल्टा टी को अगर आप कॉमन ले लेते हैं, तो यहाँ से एन और डेल्टा टी को कॉमन लेने पे आपको दिख जाएगा सी वी प्लस ऑफ आर, और ये तो कुछ नहीं सीपी होता है, तो एन सी पी डेल्टा टी। तो जब भी हीट के लिए हम लोग यूज करेंगे आइसोबारिक के लिए, तो उसमें हम यूज करेंगे एन सी पी डी टी टर्म। ये चीज हमें याद रखना चाहिए, और यहीं से आपको जो रिलेशन बिल्ड होके आता है वो सीपी इज इक्वल टू सीबी प्लस आर, जो हमने आपको दिखाया यहाँ से, ये रिलेशन यहीं से आता है। तो दिस इज वन ऑफ द रिलेशन विच यू नीड टू कीप इन माइंड। नेक्स्ट टर्म वी आर हैविंग दैट, अब अगर डिग्री ऑफ फ्रीडम को, इंटरनल एनर्जी और हीट को हम लोग रेशियो वाइज करके देखते हैं, तो ये एक रिलेशन है हमारे पास जो कि आगे काम देगा आपको। इसको देख लेते हैं, नेक्स्ट रिलेशन। Next relation we are having, this is this. थर्ड सेकेंड फर्स्ट सेकेंड हो गया है आइसोबारिक आइसोबारिक। ओके, नेक्स्ट वी आर हैविंग आइसोकोरिक, फोर्थ वन आइसोकोरिक। आइसोकोरिक प्रोसेस का मतलब होता है वॉल्यूम कांस्टेंट, वॉल्यूम कांस्टेंट। तो वॉल्यूम कांस्टेंट जब भी होगा, तो इस केस में डीवी का वैल्यू जो होगा, चेंज इन वॉल्यूम होगा ही नहीं, तो डीवी अगर नहीं होगा चेंज, तो दैट मीन्स कि जो वर्क डन होगा दिस विल बी जीरो, नो चेंज इन वॉल्यूम हैपनिंग हियर। तो जो भी आप हीट सप्लाई करोगे वो किधर जाएगा, वो यहाँ पे एन सी वी डेल्टा टी, दिस विल बी योर चेंज इन इंटरनल एनर्जी, दिस विल बी योर चेंज इन इंटरनल एनर्जी क्यू। तो यहां से आप सीवी को निकाल सकते हैं, सीवी इज डिफाइंड हियर आल्सो, दिस इज डेल्टा यू डिवाइडेड बाय n times of delta t. This is CV relation you can write here. Now isocoric is isocoric process में ये चीज ध्यान रखेंगे कि वर्क डन जीरो होगा, और जो हीट आप सप्लाई कर रहे हैं वो हीट जो है आपका टोटल चेंज इन इंटरनल एनर्जी में जा रहा है। आइडिया आइसोबारिक में हमने देखा था कि जो भी हीट हम लोग सप्लाई कर रहे हैं, तो वो हीट जो है आपका वर्क डन में और चेंज इन इंटरनल एनर्जी दोनों में जा रहा है। इसमें बस चेंज इन इंटरनल एनर्जी में जा रहा है। Now there is a term what you can say there, this in note you can write this relation. This is very important relation, that what is the change in internal energy ratio with the degree of freedom. And once you do this ratio, it will be nothing but it is work done divided by 2. And this is in terms of heat also, it is Q divided by F plus 2. So this is one of the relation which you need to remember. And you can relate and you can find out if you know the work done, you can use this relation to find the delta U in terms of degree of freedom. And once you know the gaseous atom, you can write the degree of freedom also. So this relation is very important. On the basis of this relation only, you can have that fractional change. Sometimes it is asked that it is fraction of total heat converted to internal energy. So you can see it is asking fraction of total heat. So what does it mean that what the change in internal energy is happening with respect to heat it is. So you can see a delta U by Q if I'll go for, so it is F by F plus 2, and that is nothing but it is 1 by gamma. 1 by gamma. Where gamma is in terms of degree of freedom, if I'll write that gamma is 1 plus 2 by F. This relation, or you have gamma relation that we know that it is Cp by Cv. So that is based Cp in terms of Cp and by Cv, if you write here it is, so this will be gamma. This is one relation which you need to keep in mind, that gamma it is. In terms of degree of freedom also, I have discussed that how you can relate the gamma with the it is Cp by Cv, and Cv you can write in terms of degree of freedom. It is Cv we can write in terms of degree of freedom. It is F by 2 times of R, this one. And gamma you can write like this also. You can write gamma as 1 plus 2 by F, where F is degree of freedom. This also you can write. So this relation, and this Cv relation, these three relation you have to remember to have good hold on the that formula. It is, you can remember the formula, you can solve it. Then this is first term which you need to remember here, that important part. And the second important part is, sometimes it is asked you what will be the fraction of total heat converted into work. So work, if it is asked you into work, that means this is asking you work done divided by the Q. So it is work done divided by the Q. This is the fraction of heat energy, total heat energy converted into work, that you can find out. And this is nothing but, if you go for this relation here, you can see this work by, if I'll go for Q by W, so it will be F plus 2 by 2. Once you solve that one in terms of gamma, you can write it is, so it is in terms of gamma minus of 1 by gamma. This will be the result you'll be getting. So these are the two questions which can be asked, that sometimes they ask you what the total heat we are providing to the gaseous, how much it is getting converted, how much means fraction of in total heat is getting converted into internal energy or getting converted into work. These are the two things you need to remember in terms of gamma. Then the next concept we are having, that isothermal process. This is the next one. It is isothermal process. So when an isothermal process means that it is temperature is constant, temperature is not getting changed, so temperature will be constant. Temperature will be constant. If temperature will be constant, then what are the parameters that you need to remember that it will be? So whenever we have PV is equal to constant value, that you can say it happened that no change in temperature, dt will be 0. If PV is constant, because PV is equal to an RT, and R constant value only. So if T is not getting changed, so PV is constant. And this happened when we have dt 0, no change in temperature, then we can say that whatever the internal energy change will be, it will be 0 only. No change in internal energy. And what about that? If no change in internal energy, what about the C value you will be getting here? C means that a specific heat, value will be, if it is not changing, that it will be tends to infinity. So this is a molar heat, molar specific heat capacity it is, and that will be infinity. We have that relation PV is equal to nRT. And on the basis of this relation, you can see here what we can write for P. It is nRT by V. This is the P relation we can write. So how to calculate the work done in isotherm? Work done in isothermal process. So work done in isothermal process, that what the work it will be total, because of the internal energy we are having no change in internal energy. So what the heat it will be total converted into work only. So work and heat you can write like the same it will be, and it is an R, and then T we are having log value, then it is V2 by V1. How I have written this one? Because of the work done, we know that it is P dV. Integration of this will be work done only. P we can write like this. It is nRT and divided by V. So it is dV by V. Integrate it from V1 to V2. So dV by V is ln V. Ln V means ln V2 by minus ln V1. So it is ln V2 by V1. This you can write. Now we know that this relation we can change in terms of pressure also, because here it is PV is constant. So what the relation we are having, P1 V1 is equal to P2 V2. So from here you can have the V1 V2 by V1 as P1 by P2. So this relation you can write like an RT, and then ln means log base E, and it is P1 by P2. You can write over here it is. So this is the second relation in terms of isothermal process work done. When it is pressure is given to you or volume is given to you, you can use this relation for volume pressure for this one. And when the logarithmic relation of log base 10 it is needed to write, then you can write like this is 2.303, and then it is nRT log base 10 it is, and then V2 by V1. In the same manner you can write for pressure also 2.303 nRT, then we have log base 10, and it is P1 by P2. So these are the relation in terms of isothermal process, what you need to remember. And these are the things in terms of isothermal process. Whenever we have isothermal process, and it will be pressure and volume graph will be rectangular hyperbola, it is because PV is constant. So you'll be getting pressure and volume graph as rectangular hyperbola. Next, we are having adiabatic process. So this was the isothermal process, and before that we are having isobaric. So this was isothermal fifth process. Then we have sixth. This is adiabatic process. Adiabatic process. So whenever we have adiabatic process, by that time you need to remember that heat is not getting changed. Heat will be constant. Heat will be constant. If heat is constant, that means that whatever the container inside heat is there, that outside heat is there. It is not, there is no any change in heat energy from inside to outside. That means it is adiabatic process. And if it is, we say that no heat is getting from one wall to the other wall, that kind of wall it is called diathermic, that no heat is getting transferred over there. That is the meaning, it is adiabatic. So in case of adiabatic, what the equation of adiabatic process we are having, that is equation of adiabatic process. Equation of adiabatic process, this equation we are having, that it is PV to the power gamma, it is constant. This is one of the equation which will go for the further it is, but next we know that there is no any change in heat here. So as heat will be zero, so whatever the we are having in this case heat zero means we can say NC delta T is zero. And we know that here delta T is not zero, N is not zero. So we can say there C is equal to zero. But in C is, in this case, we are having zero. But in the case of isothermal process, you have seen that C is here, it is infinity. So in case of isothermal, it is infinity. But in this case, we are having C zero only. This you need to keep in mind, that why C is getting zero if it is adiabatic process, because of sorry, no heat is getting transferred. So what the work done is happening here, it will get nullified by the change in internal energy. It will get nullified by the change in internal energy. That is the meaning of here work done. So whenever we have adiabatic process, in that process, what the work we are doing here, that will be getting balanced by the change in internal energy. So both are getting nullified to each other and making no heat exchange over there between system and surrounding. So it is called adiabatic. So whenever we have adiabatic process, what what we can do to calculate the work. We can calculate the work in terms of change in internal energy, and it is nothing but NCV delta T. Here it is. And in terms of gamma and R, we know that what is CV value, it is in terms of gamma, and R, it is CV value is R by gamma minus 1. So this you can write N and then R divided by, it is gamma minus of 1. And then we have it is this delta T, here it is T2 minus of T1. T2 minus of T1. So this is the process, this is the work done in case of adiabatic process. Whenever it is needed, you need to remember this one. And if you want to make it positive one, so you can write in terms of this way, you can write it is NR, then 1 minus of gamma, 1 minus of gamma. Then we are having this is T2 minus of T1. Rather, you can write like this, or you can write like T1 minus of T2 and gamma minus 1 only. So it depends upon you which one you remember. But this is the main form which you need to keep in mind. Now we are having remain with one polytropic process, and which will be resemble with the adiabatic process, but exactly it is not adiabatic process. And that is what you need to keep in mind, that this is not adiabatic process, but it is resemble, and only need to remember that how to calculate the work done in polytropic process and what is the molar heat capacity. Because in case of adiabatic process, we have seen that the molar heat capacity is 0, but in case of polytropic process, it won't be 0. So what kind of polytropic process? Normally it is asked already. The question is asked in J-main and J-advance also. So you can see that how you can distinguish that the process is polytropic or it is adiabatic. So whenever we have polytropic process, so whenever we have polytropic process, the format or the equation of polytropic process will be like this. It is PV to the power some X, it is constant. X, it is constant. So this PV to the power X, if it is constant, then how you can write the work done here? So you can see what the work done I have written here. This is the way, same way we can write here it is. Same way, here it is, this is in the form of NR delta T divided by 1 minus of gamma. So in the same way, I'll write here also, but this is not polytropic. So here we don't have the gamma value. Here it is X only. So we can write here what the work done in case of polytropic process will be. It is W will be NR times of delta T divided by 1 minus of X only. Why X? Because at the place of gamma, you can replace here what the power Fx is there. That is the same thing you can write over there to calculate the work done by the gas. Here it is. Now the main thing, this is the first thing which you need to remember in case of polytropic process, how to calculate the work done. And then second point, molar heat capacity will be 0 in adiabatic process, but here we don't have molar heat capacity 0. I'm writing the final result, it is molar heat capacity, and this is actually derivation here. So we won't go for that one, already video is so much longer to revise it is. So here C molar heat capacity, you can remember it. Remember it is CV plus R divided by 1 minus of X. So this is the way you can write the molar heat capacity whenever we have the polytropic process, like PV to the power X is 0. As PV to the power X is constant over there. So this is kind of polytropic process. Sometimes you'll be getting like this PV to the power 2. So this is the thing you can remember here, it is 2 or maybe 5 or something, anything which is not in the form of gamma, which is not the gamma actually. So by that time, you need to understand this is not the adiabatic process, this is polytropic process, and on the basis of that, you can get the result work done and the molar heat capacity. Normally, it is asked for. Now we have the last process to understand that what is it called, that this was adiabatic process. But the seventh one we are having. Seventh one we are having that we are having seventh already. Already we done seven. Now let's see, it is first process. It was first process here. It was melting. Second boiling. Third we are having isobaric. Fourth we are having isoporic. Fifth we are having isothermal. Sixth adiabatic. Then seven. This was seventh only. So this was seventh polytropic process. Now we are having eighth process. That is the last process to understand. So this is called cyclic process. Cyclic process. Cyclic process means that we are having the thermodynamic parameter like pressure, volume, and the temperature it is. So system returns to its initial state. That is the meaning of cyclic process. If the system returns to its initial state, if the system returns to its initial state, then we say initial state means pressure, volume, and temperature, what it was at initially. It is same. So for overall, if it is we are getting the same initial state as the final one, and the initial was there only. So in that case, we can say for overall process, overall means cyclic process. Overall process, we can say here, for overall process, we can say here that delta T will be 0. Why 0? Because what the initial temperature, it is the same final temperature. So delta T will be 0. If delta T will be 0, we can say that no change in internal energy, that internal energy change also 0. So if internal energy is 0, then we can say that according to the first law of thermodynamics, what the heat we are supplying, it is getting change in the work done by the gas only. No change in internal energy. So this is the major thing you need to keep in mind that there, and I think it is everything I have covered over there to go for the this thermodynamic process. Here it is. Now after this cyclic process, we are having indicator diagram, which I have already discussed that how to calculate the work done by the indicator diagram. Now we have the that second law of thermodynamics, or what we can say, Carnot engine. So next topic we are having Carnot engine. So in Carnot engine, you need to remember two things, that one is heat supplied and the heat rejected. Heat supplied and the heat rejected. So basis of that, you can get the, it will be this diagram I'm making here so that you can understand that Carnot cycle or the Carnot engine cycle are mainly isothermal and adiabatic process here it will be. So let's suppose this is the diagram you can make of this is working substance I'm considering here. And on working substance, there is, this is the heat we are supplying over there from the source. This is what it is called, source having temperature T1. And some work is happening over there, that this is the work, here it is. And then some other heat is getting from this working substance over there, that is Q2, and this is what it is called. This is called sink temperature will be T2. So here you can see this, this is kind of engine, it is Carnot engine in which working substance will be there, that is called ideal gas. And that draws some heat energy from the source, it is, and then we say that energy draws by Q1 it is, and then perform some work over there and then rejected. So this is the heat what we are taking to the substance, and this work is happening over there. It is after work, this is the heat rejected. This is Q2 and Q1. So Q1, what you can say, it is called heat supplied. It is heat supplied. And what about Q2? Q2 is heat rejected. Heat rejected. So on the basis of heat rejected, you can see if 100 joule per second is working substance taking, here it is, and rejected is 20 joule per second. So what you can say, work will be done 80 joule per second. So what the heat we are supplying, some work is happening over there, and the remaining energy is getting into heat rejected part. So how you can calculate the work? So it is, we have the heat supplied, we have heat supplied is Q1, and then we have heat rejected. So heat rejected is Q2. So what will be work over here? Work will be, it is simply, we can say, heat supplied minus of heat rejected. That much amount of energy is converted into work here. And on the basis of this work, you can calculate that percentage efficiency. How you can calculate percentage efficiency? This percentage efficiency, this is called eta. So this is nothing but what the work is happening. Work is kind of output. It is output, kind of output. And what the heat we are supplying, this is kind of input. So efficiency is output by input only. So this you can write here, it is, this is work divided by the Q supplied, what the we supplied over there. This is called your efficiency. Once you multiply this with the 100, you'll be getting percentage. So what we are getting here as work as Q1 minus of Q2. So it is Q1 minus of Q2 divided by Q1, and then you can multiply over here, it is 100. So this will be the efficiency. So efficiency, you can write it is 1 minus of Q2 by Q1 into 100. Now you can see Q2 is called sink temperature, Q1 is called that initial temperature or source temperature. So what the sorry temperature I said, it is heat sink का जो heat energy है, that is the heat energy. So heat rejected जो है वो sink में जा रहा है आपको, और Q1 से heat जो आ रहा है, that is one heat. So what is the efficiency? It is 1 minus of sink heat and divided by source heat. So ये चीज आपके दिमाग में रहे. In terms of अगर हम temperature लिखना चाहें, in terms of temperature, here one thing you need to keep in mind that T2 is less than T1. T2 is the temperature which here we are having the sink temperature, and T1 is the source temperature. So sink temperature कम है source temperature से. तो in terms of अगर temperature इसी को लिखना हो तो how you can write efficiency in terms of temperature? This is 1 minus of T2 by T1, this one, and multiply it with the 100. This is called efficiency. This is called efficiency. So here you have one relation of this one. You can relate Q1, Q2, T1, T2 in this relation, that if it is given to you Q1 divided by T1, this will be Q2 divided by T2. This relation you can remember, and it is W divided by T1 minus of T2. This is one of the relation which you can remember, but mainly the question normally asks you with respect to the temperature, sink temperature and the source temperature, how you can find the efficiency. And with respect to the sink heat and the source heat, how you can find the heat efficiency over there. So two forms you need to remember for finding efficiency. Then we have next, it is refrigerator and the heat engine to understand over there, that heat, refrigerator and heat pump. So next topic we are going for that refrigerator. We have that refrigerator. It is, let's see, it is refrigerator. So in refrigerator, suppose we are having that hot reservoir there, and then cold reservoir there, and compressor will be there. So in refrigerator, what is happening? The concept you must be knowing that what is the concept. If I'm considering that let W work is done on the working substance, and let's suppose Q2 heat is absorbed. Q2 heat is absorbed from lower temperature, T2, and Q1 heat is rejected to higher temperature T1. You must have seen the refrigerator, that from backside of the refrigerator there is some heat energy getting ejected out. That heat energy is rejected heat energy which is having the higher temperature rather than the whatever the temperature inside the refrigerator it is. So this rejection of the heat is happening at the higher temperature, rejection of the heat. But in case of this previously, you have seen that in case of this one Carnot engine, that rejection of the heat is happening at lower temperature. So this is somewhat opposite to that one. What it is called refrigerator here. That heat is getting rejected at higher temperature and heat is getting absorbed at lower temperature. How it is, that is the concept of compressor here it is using. And you'll be having the coefficient of performance for the refrigerator. It is how you can find out. So this is the diagram that, let's suppose this I'm considering hot reservoir, and here we are having compressor, and from hot reservoir this is compressor it is. Some work is happening over there, that work W, and this heat is getting extracted or getting absorbed there from the cold reservoir. This Q1 I am considering here, it is Q2. This is cold reservoir. And here temperature is from cold reservoir, this is T2. And here hot reservoir, this temperature is T1. T1 is greater than T2. This I have mentioned here also. This you need to keep in mind because of the hot and this is cold. So in case of refrigerator, let's suppose W is the work done on the working substance here happening, and Q2 is the heat is absorbed from the lower temperature end. And lower temperature end is having temperature T2, and Q1 is the heat rejected over there at the higher temperature T1. In that case, in this case, what the things it is asking you is coefficient of performance is the first topic, which is mainly it is ask you that what is coefficient of performance. So this is by definition, if you write here, this is coefficient of performance. So coefficient of performance can be represented by beta it is, and it is by definition, you can say heat extracted from the cold reservoir. Heat extracted from cold reservoir, and then it is divided by work done by the whatever the work happening here. So this work on the substance it is, how much work is happening. So you can see here work, we know that how to calculate work, it is Q1 and minus of Q2. This one is the heat, what here it is heat rejected and heat absorbed over there. So Q1 minus Q2 is the work here you can calculate over there. So that is the work. And what is the heat extracted? Here it is heat extracted is Q2. Q2 is the heat extracted, which I mentioned in the language here. It is W is the work done on the working substance, and Q2 is the heat absorbed over there from the lower temperature end, that is T2. So this Q2 divided by the work total, and work total is Q1 minus of Q2. So this is called beta here, coefficient of performance of the refrigerator in terms of, if you want to write this in terms of T1 and T2, so you can replace Q2 as T2 and Q1 as T1 and Q2 as T2. The same manner you can write it is, so it is T2 divided by T1 minus of T2. This is one way to write. And in terms of efficiency, if you want to write this as, then you can write in terms of efficiency with that it is 1 minus of eta by eta. So this is also one way to write the beta value. This is also one way to write the beta value. So coefficient of performance here, you have three forms to remember: one in terms of heat, one in terms of temperature, one in terms of efficiency. And Q1, Q2, you know that it is Q2 is the heat extracted from the cold temperature. Q1 is the heat rejected at the this higher in the rejected heat temperature T1. Sorry. Next topic, last topic, which of this chapter, it is this video, we are having heat pump. So it is heat pump. In case of heat pump, there is one term which you need to just remember, that is just difference of that coefficient of performance in terms of beta. It is just reverse of that. That is why it is called heat pump. It is denoted by R, small r here, and that coefficient of performance for heat pump you can write So this is mainly heat pumped to the hot reservoir. It is whatever the heat is getting pumped from the hot reservoir to the hot reservoir with respect to the work, what is happening, that is called coefficient of performance. This is, so R is called heat pumped to hot reservoir divided by total work, whatever the total work is happening. So this is what you need to remember, and this we know that what is heat pumped out to the hot reservoir. It is here. It is Q1. So it is Q1 by W. Beta was Q2 by W. See here, beta was Q2 by W, and here it is Q1 by W. So that is the only difference here. You can say this is heat pump is working over there on the basis of heat rejection with respect to the work it is. So Q1 you can write like the same. It is Q1, and the work we know that it is Q1 minus of Q2. Here it is. Heat rejected and the heat absorbed over there. So that is the thing you need to keep in mind. And on the basis of temperature, if you want to write this R value, you can write the R value in terms of temperature. It is T1 divided by T1 minus of T2. And that you can write in terms of efficiency also. So this is one way to write. This is another way to write. And the third way, you can write R as it is 1 by efficiency of where what is efficiency? It is written like 1 minus of T2 by T1, or you can write it is 1 minus of Q2 by Q1. This one. This is the efficiency which you need to remember. That's it. These are the only topics and only concept you have to keep in mind to have good performance in JMN. Just remember it and then practice and revise the concept which there in the previous year question bank, so that it will be, you can enhance your performance and you can do well over there. I hope it is clear that I have covered all the topics of heat and thermodynamics. So completed first three video I have already uploaded. This is the fourth video, will be uploaded soon. It is. So hope you can do the 3 to 4 question in the coming JMN exam. And after this, we'll be starting that it is oscillations and wave, then we'll go for the sound chapter. So this, from there also you'll be having 3 to 4 questions. So from two chapter of the 11th, you'll be having 6 to 7 question, damn sure, out of 25 questions. So if you command over there, these are the chapter from which they won't make any difficult kind of questions, so that you won't be able to solve. You can easily solve once you are gone through the basic concept or the things which is related over there, and the formula, if there is in your mind, you can solve over there. Thank you.